Alright, spending a lot of time in this classroom this weekend. I'm going to shoot a video for section 12.8. The syllabus, at least for this semester, on it says you can do problems 9, 11, 15, and 19. I decided against doing those. The numbers that you see in those problems, that letter P stands for a permutation. And somehow this sort of symbolism, or this, there's some of the problems in this section can be solved two ways, and the second way that I'm not going to show, it involves what I'm skipping in problems 9, 11, 15, and 19. All of the problems in this section ask a question of how many ways can something be done. And every problem in this section can be done in a manner that was similar to how we determined the number of elements that were going to be in a sample space by making lines and putting time signs between the lines and numbering multiplying the different possibilities. That strategy, once we get to the section, it'll make more sense. That strategy will work for every problem. Whereas the introduction, the author introduces a new concept that will work for a few of the problems, but not all of the problems. So I decided, since there is a method that every problem in this section can be solved by, that I might as well just do the method that will work for every problem. And kind of focusing on the section this way, just picking the one strategy to solve, I think it'll make it a tolerable section. Real important as I get through this section, no problem, when I do any problem, no problem is going to ask the question, what is the probability? When I see the question, what is the probability, immediately I think I'm going to make a fraction. And because no problem in this section says what is the probability, there won't be any fractions in my answers. Every problem in this section has something, if not specifically the words how many ways can this be done, something that's similar to how many ways can this be done. Every problem in this section is basically just computing a size of a sample space, and for every problem in this section I'm going to solve by making lines for as many items that I need to select. Might put words under the lines, and then above the words I'm going to put numbers, and I'm going to multiply those numbers to solve the problem. When I get into the problems here in a few seconds, you'll see what I mean. So the problems that we're going to do in section 12.8, the author could have done when we did section 12.5, where we did sample space problems and made tree diagrams. The sample spaces in this particular section are too large to construct, but we can still tell how many numbers or how many elements would be in the sample space. So I went ahead and just typed up the problems, not because I can type terribly well, but I thought it would make it easier for me to lecture, because as I glanced at some of my videos, when I had the book open, you couldn't necessarily read what I had there, but and if you had the book in front of you, that wouldn't be so bad. But this we can go through maybe even without having the book open. You need to have your calculator, because the numbers in this particular, the answers, the number answers to each of the problems can get rather large. So I brought my calculator. So anyways, this particular problem says to use an automated teller machine, you must generally enter a 4-digit code using the digits 0 through 9. 0 through 9 consists of 10 numbers. I added that. The numbers 1 through 9 are 9 numbers, and 0 is a 10th number. And there it is. How many 4-digit codes are possible? And then the author might kick in a new word. If repetition is permitted, that means any letter can be used more than one time. So once I use a letter, I'm still allowed to use it. That's kind of like with replacement. So repetition is in this section equivalent to with replacement in our earlier problems. So to answer a question of how many, I'm going to make, in this case, 4 lines separated by time sign. The reason I'm making 4 lines is because I'm trying to make a 4-digit code. And when I make a 4-digit code, there's going to be a first number, a second number, a third number, and a fourth number. When I go to place the first number, I can pick any of the numbers between 0 and 9, which is 10 numbers. So there's 10 choices for the first number. If the author would have said if repetition of digits is not permitted, then after I picked a number, it wouldn't be available to use again, and I would have to increment down. My second digit would only have 9 numbers to choose from. But because repetition is allowed, when I go, no matter what number I picked for my first number, say I picked 7, I could still pick 7 again for my second number. So there's going to be 10 numbers to choose for the second number, and regardless of what I pick for the first 2 numbers, those numbers can be used again and again. So for each of the digits, each of the numbers I need to place, there's 10 different numbers possible. And if I multiply 10 times 10 times 10 times 10, that will give me how many 4-digit ATM codes there are. So I'm going to go 10 times 10 times 10 times 10, and I get 10,000. So there are 10,000 different ATM codes possible. So if your ATM code has 4 digits in it and somebody steals your card, your debit card, and they walk up to a banking machine, the chances of them guessing your PIN correctly are slim, because there's a 1 in 10,000 chance if you enter 4 digits that it's your correct PIN. But it's not a probability question, so I'm not making any fractions. This is just how many doesn't imply fractions. 22 is similar. For every problem in section 12.8, I'm going to read through the problem and figure out how many items I'm selecting, and I'm going to make dashes for the number of items I'm selecting, separated by times signs. If I want, I'll put names under the dashes, and then once I have the dashes with names under them, I'll put numbers and I'll multiply them together. So I read through the problem. This talks about a daily double at a racetrack. It consists of picking the winning horse on both the first and the second race. It says the first race has 7 entries, the second race has 8 entries. How many daily doubles must you purchase to guarantee to win? So to be a winner, you have to pick the winner for the first race, and you have to pick the winner for the second race. So there's just 2 things I need to select. I need to select the winning horse for the first race. I need to select the winning horse for the second race. Now above these, I need to put numbers that are appropriate. Hopefully you could maybe pause the video, put the numbers in, and finish the problem. But if you're not ready for that yet, I'll put the numbers in. The first race, there are 7 possible horses that could win it. So there's any one of 7 horses that can win the first race. Those horses won't run the second race, but the second race itself has 8 entries, and there's 8 different horses that can win the second race. So if I want to guarantee myself to win the daily double, I have to purchase 56 tickets. Basically, I could have the first horse in the first race, first horse in the second race, the 1 and the 2 horse, the 1 horse in the first race, the 3 in the second, and so forth. There'd be 56 combinations of picking a horse from the first race and the second race. If I bought all 56 tickets, I'd be guaranteed to win with one of the tickets, and the rest of the other 55 would be losers. All right, so again, I read through the problem, find out how many items I'm placing, separate, make some dashes, separate it by time signs. I throw some words under the dashes just so I know what's being placed in those, and then I multiply. So 24, a password to log onto a computer account consists of 3 letters followed by 3 numbers. Determine the number of passwords possible if repetition is not permitted, repetition is permitted. So the password needs to look like this. It needs to be letter, 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 and then number, number, number. So very specifically, my password has to be exactly that format. 3 letters followed by 3 numbers. So letters first, numbers second. And then I have to know that there's 26 letters in the alphabet. And the author didn't say anything about an uppercase being different than a lowercase, so I'm assuming that my password's not case sensitive. And for the numbers, there's 10 numbers. The numbers 1 through 9, and then 0 makes 10 numbers. If repetition is not permitted, when I go to place my first letter, I can pick any of the 26 letters in the alphabet, but repetition is not permitted. Once I've picked a letter, I can't use it again. So for my second letter, there's only 25 letters to choose from. And then for my third letter, I've already picked 2 letters. There's only 24 letters to choose from. Once I pick my 3 letters, I'll pick my 3 numbers. For the first number, I can pick any of the numbers between 0 and 9, which are 10 numbers. I'm not allowed to repeat a number, so once I pick a number, I only have 9 left to choose for the second. And once I pick 2 numbers, I only have 8 left to choose for the last. Now I'm going to multiply all these. Hopefully my calculator doesn't put me into some sort of scientific notation. My calculator says how many passwords like this are possible. It's 11,232,000 passwords are possible if you're not allowed to repeat letters and you're not allowed to repeat numbers. Part B, I want to form the same kind of password, but I'm allowed to repeat letters, so I could have double or triple letters, and I'm allowed to repeat numbers, so I could have double or triple numbers. When I go to answer this question, there are 26 letters to choose from the first letter. There's also going to be 26 letters for the second letter, because once I use a letter, I'm still allowed to use it, and 26 letters for the third, because once I use a letter, or 2 letters even, I could use them again. Similarly for the numbers, there's 10 numbers to choose from for the first number. Because I'm allowed to repeat, there's still going to be 10 for the next 2 numbers as well. So I'm not incrementing down. If repetition is permitted, every letter spot has a choice of all 26 letters. Every number spot has a choice of all 10 numbers. When I multiply these numbers, 26 times 26 times 26 times 10 times 10 times 10, I get 17,576,000. So there's a lot more passwords possible if repetition is allowed. 26 is not really different than 24. It's the same sort of problem. I read through the problem. I find out how many spaces I need to fill, put a time sign between the places, and then put numbers in those dashes and multiply them. This talks about making a social security number of 9 digits. So I'm going to need to place from a first number, a second number, a third, a fourth, all the way to a 9th, a 5th, a 6th, a 7th, an 8th, and a 9th. So there's 5th, 6th, 7th, 8th, 9th. So there's 9 numbers that make up a social security number. Now I read through the problem to try to figure out what numbers go in the blanks between the time sign, and the author is going to clue me into what I need by using this word repetition. When the author says repetition of the digits is permitted, so any number I use can be used over and over again. So every single time I'm going to have 10 choices. Didn't leave myself a lot of room. This is fortunately something I can multiply in my head. This is going to be a 1 followed by 9 zeros when I multiply it. Because when you multiply tens, you just add zeros. It's going to be 1 billion. If I do this on my calculator, it's going to be tricky. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And my calculator, oh, I should have done 9 anyway. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And my calculator gives me that number. Hopefully it has the same number of zeros. '28's another horse problem. Talks about a trifecta. A trifecta is within one race picking the first place horse, second place horse, and third place horse in that order. You have to pick the first horse to be first, second to be second, and the third place to be third. And then how many tickets must you purchase to guarantee a win? Well, I must make the right first place horse. And I also have to pick the right second place horse. And I even have to pick the right third place horse. And there's 7 entries. So there's 7 possible horses that win. once a horse wins, he can't also come in second place. So once a horse wins, there's only 6 horses to pick for second place. And once there's a first and a second place horse, they can't come in third. There's only 5 horses for the third place. If I multiply these are how many tickets I'd have to purchase to guarantee winning a trifecta. That would be 210 tickets. So hopefully you're starting to get kind of into some sort of groove for this. I read through the problems, I figure out how many dashes I need to make, put timestamps between the dashes, and then figure out how many entries need to go in each position. The things that can happen is the numbers could be stagnant or the numbers can go down. And anytime the author says repetition is permitted, the numbers are going to be stagnant. Repetition is not permitted, the numbers are going to decrease. But sometimes, like in this problem, it didn't say anything about repetition being permitted or not, but I did this problem like repetition wasn't permitted because the same horse can't be first, second, and third. Once a horse is first, it can't be second or third. So by default, this is like a repetition is not permitted, even though the author didn't specifically use those words. So I have to kind of clue into the English in the problem to understand if I have to use 777 or if I'm incrementing down. All right, so the next problem, I don't know what problem it is, but it is, well, I suspect, since I just did problem 28, I suspect this is problem 30, but I didn't take the time to write problem 30 down, so I'm banking this is problem 30. And in problem 30, there's a circle drawn, a square drawn, a triangle drawn, a pentagon drawn, and a half circle drawn, and they're colored with different colors, but when I read the questions that the author asks with regards to these figures, none of the questions made any comment about color like we did in some of the last sections where the author, if something was yellow, it was going to be significant. In this particular problem, it's not going to be at all, the color is not going to be important. So when I read the problem, the author asks me, how many ways can the 5 figures be ranged from left to right? So what I'm going to do is I'm going to place these 5 figures down from left to right in some sort of order. And I need to make my first figure is going to go. And when I go to place my first figure, I can pick any of the circle, square, triangle, pentagon, or half circle. There's 5 choices for my first figure. I'm assuming that once I pick a figure, that it's in place and I can't pick it again. So like if this first figure was a triangle, when I go to place the next shape, so if I place a triangle first, I couldn't place a triangle again because I'm only placing these 5 figures. I'm not allowed to duplicate. Even though the author didn't say we aren't allowed to duplicate, I'm assuming each one of these spots just needs to get one of the shapes. And so for the second spot, once I've picked one shape, I only have 4 spaces left for the second, 3 for the third, 2 for the second to last, or fourth, and 1 for the last. If I multiply these, I can do it without my calculator. There's 120 ways, orders that I can place these in. If I'm going top to bottom, like I could go, circle, triangle, square, half circle, pentagon. Placing something top to bottom isn't any different than going circle, triangle, square, half circle, pentagon. The author is just trying to be cute here. The answer for this problem, there's 5 figures to choose from for the top figure. And then once I pick the top figure, I can't pick it again. So there's 4 figures to choose from second place. And then in the third position, third from the top, there's 3, and then 2, and then 1. And I get the same 120 different ways I can place them. So placing them left to right isn't any different than placing them top to bottom. There's still 5 choices for the first, 4 for the second, 3 from the third, and so forth. C and D get to be a little bit trickier. So if the author insists on a figure going in a certain spot, I need to put it in that spot first. So in part C, I'm still placing those 5 shapes, but the triangle must be placed on the far right. So for the far right, there's only one choice. It has to be the triangle. And now once I've placed the thing that absolutely has to be placed, I'm going to fill in the rest. I'm going to fill my first, second, third, and fourth shapes in. My first shape, it can't be the triangle because the triangle is already placed. So I only have the four remaining shapes to pick. So now I have 2 shapes, and I'll have the triangle and some other shape in. I pick my next, there's only going to be 3 shapes, and then 2 shapes, and then 1 shape. And if I do this, if the triangle's forced to be last, I only have 24 possibilities, as opposed to the top 2, A and B, where there weren't really any restrictions. I can put the things in any order. And so again, this is a non-repetition by default. The author didn't say I couldn't use the same figure more than once, but it's kind of implied in the write-up. And there's a part D to this. I'm going to place the figures from left to right, and the circle is going to go on the far left. So the circle's going to go here, so there's only one choice for the far left. And the triangle is going to be on the far right. There's only one choice for the far right. So the first figure has to be a circle. The last figure has to be a triangle. The middle 3 figures can be any of the remaining figures. But once I've placed the circle and the triangle, I only have 3 figures left. So for the second spot, I have 3 figures to choose from. And then once I pick one of those, there's only 2 figures left. And then once I pick one of those, there's only 1 left. If I multiply these with this restriction, there's only going to be 6 possibilities. 32, there's maybe multiple ways to think about it, but I think regardless of the way you think about 32, the answer will come out the same. So there's 8 cars sitting on a lot, 3 customers are going to pick, and each customer can pick his or her own car. How many ways can the cars be picked? So what has to do, the first customer needs to get a car, the second customer needs to get a car, and then the third customer. So the first customer is going to pick a car, then the second customer is going to pick a car, and then the third customer is going to pick a car. Ultimately, they can't pick the same car. So even if the second customer picked first, once he picks, the other people can't pick that car again. So this is a without repetition, because once a car is picked by somebody, it's not available to the other people because they're not going to share a car. So the first person that goes out to pick, they'll have 8 cars to pick from. Once they pick their car, the second customer is only going to have 7 cars to pick from. And once the second customer picks his, there's going to be 6 left for the third customer. So the number of ways they can pick these cars, there's going to be 5 cars not picked, are 336 ways. Whoa. I just woke up the lights in the classroom. I don't know how that happened. There's lights are on a sensor in here, and I had all the lights off, and now magically a light just went on, and I'll shut it off. Not that I don't know if it's messing up the video. Okay, so problem 34 talks about ISBN code numbers. And if you buy any book from our bookstore, if you try to order a book online, you can search for the ISBN number if you're trying to find the book. And an ISBN number is unique to a book. And the question is, how many ISBN numbers are possible? If an ISBN number has to have this form, each of the digits need to be a number from 0 through 9, which is 10 digits. And then it says repetition is allowed. So I'm going to make a spot, and I have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 numbers need to make up an ISBN number. Because repetition is allowed, for every single number, there's going to be 10 numbers to choose from, the numbers 1 through 9, in addition to the number 10. To find out how many ISBN numbers would be possible, that's 10 to the 10th power, which is 10 times itself 10 times, which is a 1 followed by 10 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, comma, comma, comma. So there are 10 billion different ISBN numbers possible. Once there gets to be more than 10 billion books that are registered, the ISBN numbers are going to have to change. This is like why in Phoenix now we have 3 area codes. You know, back in the day, we only used to have the 602 area code, so you wouldn't have to dial, you know, an area code when you're dialing local. But eventually, when you're dealing with 7-digit phone numbers, you use them all up. And so when all the phone numbers are about to be used up, we decided we needed to add new area codes so we can give out more numbers. So you could have, you know, a 623 number and a 602 number have the same 7 digits, but now they're a different number because they have a different area code. 36 wants a disc jockey to play 8 songs. So I'm going to make 8 slots because the disc jockey is going to play 8 songs. 1, 2, 3, 4, 5, 6, 7, 8. And each song can only be played once. That means repetition's not allowed. There are 5 fast and 3 slow songs. Part A doesn't make any differentiation between fast and slow songs. It just, he needs to play the 8 songs in any order. So for the first song, there's 8 songs to choose from. For the second, there's 7, and then 6, and then 5, and then 4, and then 3, then 2, and then 1. So I'm going to go 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And without any restrictions, there are 40,320 orders that he can play the 8 songs in. Part B gives a little bit of restriction, just like the triangle square problem. And I think I got 1, 2, 3, 4, 5, 6, 7, 8. That's all I need. It says the first song must be slow. Well, there are 3 slow songs, so there's going to be 3 songs that I have to pick from the first song. And the last song must be a slow song. So I'm playing a slow song here, and I'm playing a slow song here. Once I've picked a slow song from my first song, I can't pick it again. My last song could be one of the 2 remaining slow songs. So now the rest of the songs have no restrictions. What I have left are 6 songs. I have the 5 fast songs, and I've placed 2 of the slow songs. I have 1 slow song left. So for my second song, it could be a slow. It could be any one of the 5 fast or 1 slow left. So there's 6 songs, and then 5 songs, and then 4 songs, and then 3 songs, and then 2 songs, and then 1 song. So once I get the have-tos placed, then I can increment down what's left by 1. So this is going to be 3 times 6 times 5 times 4 times 3 times 2 times 1 times 2, and I get 4,320. So having that restriction, making the first and last songs slow, there's only 4,320. Less, like 90% less ways. C, I reminded myself there are 3 slow and 5 fast songs. It says the first 2 songs must be fast. 4, 5, 6, 7, 8. So I'm going to place these 8 songs. And I know there's 5 fast. The first song must be a fast song, so I got to pick a fast song there. There's 5 fast songs to choose from. For my second song, it also has to be fast, so I only have 4 songs to choose from because I've already played a fast one. And then for the rest of the spots, I can play any of the songs. And there were 8 songs. I've already placed 2 of them. There's going to be 6 songs left. So 6, then 5, then 4, then 3, then 2, then 1. So this is going to give me 5 times 4 times 6 times 5 times 4 times 3 times 2 times 1. And I get 14,400 ways this can be done. 37 through 40 wants to have an identification code, has 2 letters followed by 4 digits. So I'm going to go letter, letter, and then number, number, number. So digit, 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 digit. And I'm assuming there's 26 letters. Upper and lower cases won't matter to me. And 10 numbers. And repetition is permitted. So for the first letter, there's 26 letters to choose from. I still have 26 letters for my second one. And for each of the numbers, there's 10 to choose from. If I multiply these, 26 times 26 times 10 times 10 times 10 times 10, I get 6,760,000 different ways that this can be done. These problems, believe it or not, can get incredibly hard to do. Our author's being very careful in the way he asks the questions. It seems like maybe they're sort of trivial, but these are the easy version of these problems. If the author changed up the words, you might not even realize the difficulties that would arise. But trust me, these things can get crazy complicated when they look so harmless, but they can get really bad. But we don't have anything that's bizarrely odd. So first letter must be an A, B, C, or D. So I have 4 letters to choose from for the first letter, either A, B, C, or D. Repetition is not permitted. So for the second letter, I've placed a letter, either A, B, C, or D. I don't know which of the 4 I placed, but I know that I'm going to have 25 letters to pick for my second letter, because repetition is not allowed. Once I've picked a letter for the first one, I can't use it again. So there's only 25 for the second. And for my numbers, I'm going to increment down. There's 10 numbers. Once I've used a number, I can't use it again. So there's 9. Once I've used 2 numbers, there's only going to be 8, and then 7. And the answer to this, there's going to be 504,000 different identification codes if the first letter has to be an A, B, C, or D, and repetition of numbers is not permitted, or repetition of anything isn't permitted. So 2 problems left. 41 through 44 talk about license plates. License plates need to have 3 numbers, or 3 digits, followed by 2 uppercase letters. So I'm going to have a digit or a number, digit or a number, digit or a number, and then capital letter, and I'm not worried about small case letters. So there's only 26 letters to choose from. And now I have to be careful on how I read this problem. On 42, the author says repetition of numbers isn't permissible. So there's 10 numbers for the first number, 9 for the second, 8 for the third. He doesn't say anything about repetitions of letters being allowed or not allowed. Because he didn't make a comment about repetition of letters not being allowed, I'm going to assume, even though repetitions of numbers wasn't allowed, that repetition of letters is allowed. It's not clear whether they are or aren't, but because he made the special announcement about the numbers that not being repeated and didn't make a special announcement about the letters, I'm assuming the letters are allowed to be repeated. If you would have put a 25 there, I couldn't really say that you're wrong, but you just didn't, think the way the author thought. I would assume that this is what the author would want here. The second one is going to be the trickiest one that we've had yet. It would be nice if you paused the video and tried to do this. Without me doing it. And there's definitely room here for confusion. So I'm going to go through. The first digit can't be a 0, so it can be any of the numbers 1, 2, 3, 4, 5, 6, 7, 8, or 9. So it can't be a 0. The second number can be 0, and then any of the other ones that I didn't use. So like if I used 5 the first time, it could be 1, 2, 3, 4, 6, 7, 8, 9, or 0. There's going to be 9 digits to choose from for the second one, because I'm not allowed to use the first number again. The first number couldn't be a 0, so there's going to be 9 choices here. And then I'm going to have 2 numbers placed. There's going to be 8 numbers for the second. For the letters, because repetition wasn't permitted, and the author didn't say repetition of numbers, repetition of letters wasn't permitted, I assume repetition of each wasn't permitted, And that's why I went down on the numbers, and I'm going to go down on the letters. So in this one, the author only said repetition of numbers wasn't permitted. Here, the author said repetition in general is not permitted. So I'm trying to read the author's mind, and I think that's what the author wants for this problem. So if I did 9 times 9 times 8 times 26 times 25, I get 421,200 different license plates with those particular instance, those restrictions. Last problem is 51. It talks about a person going to a computer store, buying a separate computer, a monitor, a printer, which we've done something like this earlier when we made sample spaces, and a scanner. Assuming all the parts are compatible with each other, how many different systems can I make that has one computer, one monitor, one printer, and one scanner? Well, there's 5 computers, 4 monitors, 7 printers, and 2 scanners. I need one of each. If I multiply those numbers together, I get 280 different computer systems are possible. So hopefully the lectures over 12.7 and 12.8 didn't feel overwhelming. 12.7 was the probabilities with the given. 12.8 is all the how manys. Once we get into sections 12.9 and 12.10, we're going to start integrating some problems. We're going to take these 12.8 problems and answer probability questions related to them. And this is when things start to get harder at the end of the chapter. But there isn't anything in sections 7, 8, 9, and 10 that is new to those sections that would make its way onto the test. So just as long as you're doing the homework and following along reasonably well, when we get the test, it's going to be a take-home test. You should either be able to look at my video and find every problem on the take-home test, hopefully as like a problem I've done on a video. If not exactly like a problem I've done on a video, then it'll be exactly like a homework problem. So you should have, when you get to do the take-home test over chapter 12, the last 4 sections, you should have hopefully lots of reference material so that as you're going through the take-home test, you can match up the problem that you're asked with a problem that has a similar skill set. And hopefully the take-home test kind of goes reasonably quickly and it isn't that hard. All right, I'll shut this off.